going to go over stereoisomers or geometric isomers. By the end of this video, you want to be able to draw and recognize geometric isomers and explain why they can be geometric or stereoisomers. Okay, so let's just have a talk about it for a start. So when we actually have a single bonded molecule, what happens is any groups or atoms on either side of the single bond can actually freely rotate 360 degrees. So none of these substituents are either held at the top or the bottom of the molecule. They can move about easily. So we can't get geometric isomers or stereoisomers with saturated compounds. However, what we can do is if we have a double bond, then a double bond will, here we can see, hold these different groups firmly in place. So here are the two geometric isomers. They have a double bond, so it can't rotate, and these held in fixed positions. Also, each carbon has two different groups. The other side, 1, 2, that makes it geometric isomer. These are a cross, and this is trans. This has a double bond, can't rotate, but the two chlorines are on the same side, and this is a cis. So this is trans and cis geometric isomers. Now what do we mean by that? Well, because these carbons have two bonds between them, the right hand side of this molecule and the left hand side of the molecule can't rotate relative to each other. So the CH3s are always going to be held at the top of the molecule or on the same side of the double bond as each other. Now let's have a look at some geometric isomers, and in this case we're going to have a look at the geometric isomers for butyrene. So actually the first geometric isomer for butyrene is the one we've just drawn. Notice it's butyrene because there are 4 carbons in a row and the double bond is off the second carbon. But in this arrangement here, because of the double bond, the 2 methyl groups have found themselves at the top, and this is actually called this has a special name, it's called cis, but we'll just go through this first. So we can see that off the first carbon there are 2 different groups or atoms bonded to it. So there's a CH3 and there's an H. And off the second carbon there are 2 different atoms or groups, there's a CH3 and an H. To be a geometric isomer, actually you have to have 2 things. You must have a double bond to hold the atoms firmly in place, and each carbon of the double bond must have 2 different groups or atoms coming off it, so that we can get either a cis arrangement like this, okay, so this is called cis butyrene, or we can get this trans arrangement like this, trans butyrene. Now notice these molecules actually have a different shape. This is like if you were to see this molecule, it would be a U shape, and this is kind of like more of a straight line. Now, when would we have a double bond but not have geometric isomers? Well, let's have a look at this one here for propene. Now, if you look at propene here, you can see, well, it does have a double bond, and it is holding the CH3 at the bottom of the molecule. And it's holding these 2 hydrogens at the top together. However, because on the left-hand side, the carbon has 2 atoms that are the same, it cannot be a geometric isomer. We can't have a cis arrangement and a trans arrangement because actually the hydrogens are in a trans arrangement, but they're also in a cis arrangement. So there's only one version of this that we can draw. It can't be geometric isomers. So there must be 2 requirements for a geometric isomer. The first requirement is there must be a double bond, because it stops the molecule from rotating and holds the groups and atoms firmly in place. And it must have different atoms or groups coming off each carbon of the double bond. If you meet those 2 requirements, you will have both a cis version and a trans version. They are geometric isomers or stereoisomers. Okay, so what type of question are they going to ask you about this? Well, here's a question here. Explain why 1,2-dichloroPropene has geometric isomers. Draw and identify these isomers as cis or trans. Okay, so here is a drawing of 1,2-dichloropropene, and I've drawn the trans version of it because the chlorine atoms that are similar across the double bond are trans from each other. Notice that this meets the requirements. It has a double bond that stops rotation, holds them firmly in place, and we have off each carbon of the double bond 2 different groups coming off it. So that's the trans arrangement, and here's the cis arrangement. So we are trans and cis. Now we will need to explain why this is trans and cis. Well, both carbons of the double bond here have 2 different groups, atoms coming off them. The carbon 1 here has a hydrogen, a Cl and a hydrogen group coming off it, and the carbon 2 has a CH3 and a chlorine coming off it. As the double bond holds these groups in a set position, we can either get a cis or a trans arrangement as shown. So when I explain this, I actually have to explain in detail. Yes, it has a double bond that holds them firmly in place, but the first carbon has a chlorine and a hydrogen that are different, and the second carbon has a CH3 and a chlorine that are different. So I actually have to expand and explain to whoever's asking me the question how I know it's a geometric isomer. Okay, one last point about geometric isomers. You might not notice this, but chlorines are very electronegative atoms, and actually the trans molecule here is, if we were to take the center of the negative charge, it's right in the center, so this is really a non-polar molecule. But if we look at the cis one, 2 chlorines at the top means the center of the negative charge in this molecule is going to be near the top of this molecule, and it's going to be polar. And because of that, they're going to have slightly different boiling points and melting points. And actually the boiling point of the trans one is 48 degrees Celsius, where the boiling point of the cis one, because it's polar and it will have slightly stronger intermolecular attractions, it has a higher boiling point. So that's one of the important reasons we want to know the difference between, or know whether it's a cis or a trans geometric isomer. Hopefully this has helped you, and you now have a better understanding of geometric isomerism. Hey, thanks for watching this video. Hopefully this has made you more confident with your chemistry. Don't forget to like, subscribe, or leave a comment about anything that you want to with this video or any questions you have. I'll see you later.